reported.
Then we have defined what is a periodic function. That is, if we can express a function v of t is equal to v of t plus capital T, where t is called the time period, then that function is called as a periodic function. Okay, the signal is called periodic signal. A best example is the sinusoidal wave, which could be expressed, which we already know that it is got a period 2 pi. After that, we have tried to establish a relationship between this angular frequency, that is omega, with the time period t, and we have written that omega is equal to 2 pi by t for a sinusoidal function. Okay. Is a periodic square pulse or a square wave as shown. The function could be defined like this: v2 of t is having a particular value for a certain range of time, that is from 0 to t1. It is having another voltage which is equal to another value which is equal to minus v2 for the remaining duration of the time period. So the total time period is capital T. So after t, the pulse is going to repeat, retaining the same shape. Okay. So that is another example. Then we saw in detail what are sinusoidal functions. So a function of the form of cos of omega t plus or minus theta, or sine of omega t plus or minus theta, is called as a sinusoidal function. And we have seen that a cosine wave could be expressed in terms of its sine as a sine function. Then we have tried to see what is the relationship between this t and omega, as well as the relation connecting the frequency as well as the time period capital T. Also, we know that time period is nothing but the inverse of the frequency. T is equal to 1 by f. After that, we saw what is meant by time shift and phase shift. So we can shift a signal in the time domain as well as in the phase domain. So, for example, I have a sinusoidal function. Let me say that this is uh, let me call it as a sine theta. So a is the amplitude, so that the signal is now oscillating between plus a and minus a. Then I can shift it along the axis. Okay, so I can shift it along this axis. So if this is the theta axis, so angular axis, I can shift it. For example, I can shift it by an angle, say phi, such that this angle is phi. Then I can write this function as equal to a of sine theta plus phi, right? So I'm shifting it towards the right hand side. Okay. Another kind of shifting that we have seen is in the time domain. So I can express this sinusoidal function as equal to a sine omega t. I can shift it in the time domain also along the time axis. For example, I can shift it in the towards the right side. Okay, so this is called delay. That is, I am delaying that function time shift of tau seconds could be represented by v of t plus tau, which is called as the advance, whereas time shift of tau seconds, which could be represented as v of t minus tau, is called delaying of the signal. Okay. Sorry, here should be equal to theta minus phi. Okay. That is the delay. Okay, shifting in the rightward manner is represented by f theta minus phi. Similarly, for this thing, so this is the time axis. So this is, let us say, the original signal is now time delayed by some time tau. So this could be written as a of sine omega of t minus tau. Okay. So this is called time delay function. Similarly, we can advance this function by a magnitude tau, in which case the original signal is shifted towards the left side. Okay, so we will get a signal like this, and this magnitude, this amount is represented by tau, and this function is represented by a of sine omega of t plus tau. So this operation is called advancing the signal, and this operation is called delaying of, sorry, yeah, this is called delaying of the original signal. So this is time delay, and this is shifting in the in terms of the angle. Okay. Similarly, we can also shift the signal towards the left also by a particular angle, in which case, so if it is shifted to by an angle, say phi, so this is phi, then this function could be written as a of a into sine of theta plus phi. So I am shifting towards the left side. Okay. Then after that, we have established a relationship between this time shift as well as this phase shift theta. That is tau is equal to, that is the amount with which we are shifting in the time domain is proportional to the amount with which we are shifting in terms of angle divided by the angular frequency. So after that, we have said if we are having higher frequency, then the for a given phase shift, the amount with which the signal is shifted in the time domain is lesser, because as we increase the frequency, because of this relationship, tau is equal to theta by omega. Okay. Then we saw how we can combine periodic functions. So we can take any periodic function, say v1 of t. So it is periodic by definition means v1 of t is equal to v1 of t plus capital T1. Similarly, we have another periodic function. Okay, and v of t is a new function which is the sum of these two periodic functions v1 of t and v2 of t. So is it whether is it periodic? Is the new function that is the sum of two periodic functions? Is it going to be periodic? So that will be periodic if we can express the ratio of t1 and t2, that is t1 by t2, as the ratio of two integers, or in other words, the ratio is a rational number or not. So if it is a rational number, that is it will have a fixed number of decimal places, or it could be represented as the ratio of two integers. Then the new function which is obtained by adding the two periodic functions will also be a periodic function, and its period, time period, capital T, will be given by cross multiplying these values. So n1 into t1, or which is equal to n2 into t2. So we saw certain examples with respect to that numeric that concept, where we have added various sinusoidal functions having different frequency, different angular frequency. So cos of phi t and the sine of 3t. Okay, where omega is phi here and omega is 3 here. So the frequency is different here, and we are adding the signal. So we saw 3 examples for that. Then we have seen what is meant by average value of a function, as well as the effective or RMS values of function. So we can find out the average value of a function by integrating that function over the time period and dividing it by the total time period. Similarly, the root mean square or the effective value of the function could be found out by taking the square of the uh, square root of the mean of the square of that particular function. Okay, or in other words, it is called the RMS value, which stands for root mean square. So take the square root of the mean of the squares of that function. Then we saw examples in which we found out what is the average value and RMS value for a cosine function, and we saw that the average value is equal to 0. So for any sinusoidal function, the average value will be equal to 0, whereas the RMS value will have a value equal to the peak value, that is Vm by root 2. So we have derived that relationship. Similarly, we have seen the example for a half a rectified sinusoidal function, in which we have found out that the average value is equal to Vm by pi. So the average value of a rectified function sinusoid is equal to Vm by pi, and the RMS value is equal to Vm by 2. Okay, where Vm is the peak value, peak voltage or amplitude of that signal. And I left it here to do it as an exercise. So anybody tried? What is the average and effective value of this periodic function? Are you getting any answer for this question? So how can you find out the average value? So the definition is V of t, the average value is equal to 1 by the time period over the time period, integral over the time period, V of t into dt. So how does this function going to vary? Can you picturize this function? It will be like a square wave like this. Okay, so it will look like this. So from 0 to capital T1, it will have a value of V naught, and from T1 to 3T1, it is going to have a value of minus V naught. Okay, so this is how this function is going to look like. So we can find out the average value. So this is the general expression. Okay, this has got nothing to do with this thing. Okay, so in our case, the capital T will be equal to 3T1, because it is going to be a periodic function with period is equal to 3T1, and we have to integrate it over 0 to the total time period. But it is divided into two parts. For first range is from 0 to T1, in which the function V of t is having a value plus V naught. So from 0 to T1, it is having a value V naught dt, and for the period T1 to 3T1, it is having a value minus V naught. Okay, so take the limits like this. So did you try this? Are you getting any answer for this? What is integral of v naught dt? V naught is a constant, right? So you can take it out. So integrate with respect to dt. So integral of t is dt is t for the limit 0 to t1. And here also you can take out v naught and apply the limits for the integral of dt, which is nothing but t, and the limit is from t1 to 3t1. Okay, so that will be 1 by 3t1 v naught of t1 minus 0 plus minus v naught of 3t1 minus t1, right? Applying the limits, upper limit minus lower limit. So this will be 1 by 3t1. You can take v naught outside of this bracket. So here we have t1 and here we have 3 minus 1 is 2t1 with a minus sign. Okay, so here we have t1. So the total will be minus t1, right? Here we have plus 1 and here it is minus 2. So it will be minus t1. So total value will be equal to, net value will be equal to minus of v naught divided by 3. Are you getting this answer?
Yes, sir.
Yes, sir.
Okay. And you can find out the effective value also. V effective. Let us take the square of this. So it will be 1 by the time period integral 0 to total time period p square of t dt. Now apply the limits. Total time period is 3t1 and the period is from 0 to split. The period is total period is split into two parts. First period is 0 to t1, in which the function is having v naught as the value. So taking the square means v naught square dt plus integral t1 to 3t1 v naught square dt. So you can similarly you can take v naught square common outside here also. And within the bracket you will have so t integral of t dt is t 0 to t1, and here also we are having t and the limits are t1 to 3t1.
Sir, V naught is square.
Inner square is taken outside. So here we are having v naught square and here also we are having v naught square, and we are integrating with respect to t. So v naught square is a constant value, so we can take it out, and in this limit we are having, actually it is minus v naught the whole square, right? So it will become v naught square itself. So what I meant to say is that here I will have 1 by 3 t1 into v naught square integral 0 to t1 dt plus here also we are having v naught square integral t1 to 3t1 dt. Okay. Now I can take this v naught square as common outside, and I can integrate this integral dt within the limits 0 to t1, and here also I have integral dt within the limits t1 to 3t1. So what is integral of dt? It will be equal to t within the limits 0 to t1 plus integral of dt within the limits t1 to 3t2. So that is the intermediate step. After this we can come here. Now when I apply the limits, it will be equal to v naught square by 3t1 t1 minus 0 when I apply this limit t1 and 0 here plus 3t1 minus t1 and I apply the limits in the second part. Okay, here. So what do I get? Is v naught square divided by 3t1 into, so here I have 2t1 and here I have t1. So if you add it up, it will be 3t1. So it will be 3t1. So ultimately you will have v naught square as the v effective square. Okay. So the left hand side we are having v effective or vrms square. So what is the effective voltage? Sorry, effective value of this function? It will be equal to v naught. Okay. Any doubts in any step?
No, sir.
Ask me. We simply applied the formula. Only thing we have to look at the function and apply the limits. We can look at the function to know what is the time period. Okay, so using these two things, that is the time period as well as the limits of the integral, we can use the formula to find the effective value as well as the average value. So the formula is going to remain the same. So for average, in order to find the average value, we use this formula, that is 1 by t integral 0 to the time period. So t here represents the time period. Okay, integrate it over the time period v of t dt. And since we are having two values within the time period 0 to the here the time period is 3t1, and within that time period we are having two values for that function. So for time period 0 to t1 we are having the value of that function is equal to v naught, and for the time period t1 to 3t1 we are having the value of the function as equal to minus v naught. That is why we split the integral like this. So like this, using this concept, you can find out the average value as well as the effective value or the RMS value of any function. If you know the function, how we can write this function. Okay. So we should know how to write this function also. Sometimes the signal will be given like this. Then how to find the average value as well as the RMS value. So when we see the signal, we should be able to write this function also. That is the next step. Okay. Always the function may not be given as such. For example, here this example, if you see, uh, a statement is given in which a network is mentioned here. Okay, so compute the average power dissipated from 0 to t in a resistor connected to a voltage Vt. So what is the average power dissipated? So we are asked what is the P average. what is the average power. So if you know what is the power, then we can find out the average power, which is given by 1 by t integral 0 to t, the time period, the instantaneous power pt into dt. So we should know what is the instantaneous power or the function for this power in terms of t. So if you are having a resistor, what is power? What is the power dissipated in a resistor? If I am applying a voltage, yeah, V into I. So I'm applying a voltage, small v of t, instantaneous voltage, and it is driving a current I of t. Now the instantaneous power P of t is the product of instantaneous voltage into instantaneous current V of t into I of t, which is the same as V of t the whole square by R, or we can write it also equal to I of t the whole square into R. Okay, because we know that these three expressions we are familiar with. So P is equal to V into I, which is equal to V square by R, which is equal to I square into R. So we can use any of these equations, but in the question problem, it is mentioned that the voltage is given here. Okay, V of t is given. So it is better to go for that value instead of I, because I is not nowhere in the question I is mentioned. So it is better to go with the second equation. Okay, because R is a constant, right? So here P of t, the instantaneous power is equal to Vt square by R. Okay. So what is the average value of P of t? 1 by t integral 0 to t P of t the whole square divided by R dt. Okay. So that is the average power that is dissipated. Let me label it as equation number 1. Okay. I hope it is clear up to there. Now the second part is telling replace V of t by a constant voltage VDC. So what if we replace this V of t with a constant voltage, say V of DC? Okay, see, I have used capital V here because it is going to be DC voltage. So what happens to the current? Now a new current IDC is going to flow through it. Okay. Now we are asked to find what is VDC such that the average power during the time period remains the same. So when I replace the earlier problem, that is the voltage across a resistor, now I replace it with a DC voltage VDC. What is the power? That is the average power during the uh, what is this voltage VDC such that the power is going to remain the same. So we have found out the power which is given by this expression. So this power is going to remain the same, and I am just changing it to DC voltage. So what is that DC voltage which will keep this power as same? So let me call this as, say, P dash of average, the new power, where I have replaced this voltage source Vt with VDC, right? The equation is not going to change because power is V square divided by R itself, right? Understood. I have replaced this V of t with the VDC. That's the only change that is happening. So P dash average is the new power. Okay. But in the question, it is told like this P dash average is equal to P average. Now I have to equate these two equations to find what is the new voltage VDC, such that the power is going to remain the same. So I can further simplify this. How can I simplify this? This is a DC voltage. So it is a constant value. It is not going to depend on the time. Right? So I can take it out of the integral. So I can take VDC square divided by, and R is also a constant. Resistance is not going to change with respect to time. So what happens is I will have integral 0 to t dt here. So what is that? Integral of dt is t, and if I apply the limit 0 to t, it will be t itself, right? So I will have VDC by RT into T, which is equal to VDC square divided by R. So that is my second equation. Okay. So when I replace this, um, alternating voltage or voltage that is function of time with a DC voltage source, the average power is given by VDC square by R, which is already understood because we have already seen what is the DC power. So the total power is V square by R, the same expression only. Okay. Only thing here I have shown with respect to the average value, because in DC we have only the average value, right? RMS is defined only for alternating signals. Now in the question it is mentioned that you are such that the average power during the period remains the same. So it is mentioned that P dash average when we are using the DC voltage is equal to the P average when we are having a time varying voltage signal, and we have to find what is VDC. So given, so we can equate 1 and 2, right? Equating equations 1 and 2, we can write. So here 2, for 2 we have VDC square divided by R is equal to, and equating 1 here we have 1 by t integral 0 to t Vt whole square divided by R into dt. But what is this? 1 by t integral 0 to t Vt square divided by R into dt. What is this equation? Anybody? What is this value? This is our RMS value square, right? We have defined the RMS value is equal to square root of 1 by t integral 0 to t square of the function dt, right? So this is nothing but the RMS value square, VRMS square. So we can write this is equal to VRMS square. Or in other words, you have to take this R also outside. Okay, so this is equal to 1 by R. I will rearrange this and write it here. Then you will be able to understand this. So I will take 1 by R outside into 1 by T integral 0 to T Vt square dt. Okay, so this portion is V RMS. Now we have, sorry, V RMS square. Okay, now we have VDC square divided by R is equal to V RMS square divided by R, or in other words we can say that the DC voltage that we are supposed to apply here is equal to the RMS value of the AC voltage that we have already applied. So this is the meaning of that RMS value as well as the DC value. So it means that if we have a resistor through which we are passing an alternating current I of t, then the RMS value of this I of t is nothing but the DC value of this current, the DC current that we are supposed to pass through which will dissipate the same power as that of the initial case. Similarly, the RMS value of this voltage V of t is that particular voltage which when we apply dissipates the same power if the signal if the voltage sorry, if the resistor is subjected to the sinusoidal voltage or the alternating voltage. Okay, so RMS value is nothing but the DC voltage that will produce the same amount of heating power in a resistor. Okay, heating power or power dissipated in a resistor. So that is the conclusion of this. From this numerical you can understand that Vrms is nothing but equal to Vdc, that is dissipating the same power. Are you able to appreciate the meaning of this? So in exam, for objective exam, it may be asked like what is the power, what is the voltage that will dissipate this much of heat. So we should be able to understand that they are asking the RMS value of that or the DC value of that particular voltage. Okay, now moving on. The current I of t shown in figure passes through a 1 microfarad capacitor. Okay, so we are given a voltage waveform which is passing through a 1 microfarad capacitor. So, okay, so we have to find out what is the AC voltage, VAC, the voltage across the capacitor at various time instances. So one is 5k millisecond, that is at 5 millisecond. 5k means sorry, which is at 5 into k times the millisecond. So k will take a value of 0, 1, 2, 3. So when k is equal to 0, t will be equal to 0. K is equal to 1, t will be equal to 5 millisecond, like that. So we are asked what is the value of the voltage across the capacitor at these points. That is 0 millisecond, 5 millisecond, 10 millisecond, like that. At these points, what are the voltages across this capacitor? So we are given the current waveform and we know the value of the capacitor. So how can we find the voltage across the capacitor? What is the expression for voltage across the capacitor? What is the expression for voltage across capacitor if we know the current?
I is equal to C dV upon dt.
Yeah. I is equal to C dV by dt. So we need V. Okay. So we can find out what is V, voltage across the capacitor, which is equal to 1 by C integral it dt, right? Here we are given the current waveform I of t, which is a square pulse as we can see in this figure, and the C value is given and I is given. So we can directly substitute here. So what is C? 1 into 10 power minus 6 microfarad into I. So how can we write this I? So initially, before this, I had told sometimes the value of the function will be directly given. Sometimes it may be given the waveforms. So we should know how to write this function. How can we write this I of t? This is square pulse, right? And I of t is carrying is having a value of 4 milliampere for the time period 0 to 3 millisecond, right? Okay, so it is having a value of 4 4 milliampere for time between 0 to 3 milliseconds, and it is having a value of minus 2 milliampere for time ranging from 3 millisecond to 3 millisecond to 5 millisecond, right? And it is a periodic waveform, as you can see. It is having a period t, capital T is equal to 5. So time period t is equal to 5 millisecond, as you can see here. The same waveform is repeating after this point. So this is a repetition of the first wave that we have seen. Okay, so that is understood. Okay, this is repeating like this. So this is a periodic wave. So we can write the function like this. So this is general expression for the voltage across the capacitor, provided we know what is the current I of t. So in our case, so let me label this as VC. This is our equation. In our case, the voltage is equal to 1 by, and the capacitance value is 1 microfarad. So C is 1 into 10 power minus 6, and I of t has to be integrated from, so first let us find what is the voltage that is V voltage across the capacitor at t is equal to 5 millisecond. At t is equal to 5 millisecond. Okay, so I can label this as say VAC of 5. VAC 5 millisecond, or VAC t is equal to 5 millisecond. Okay, I can label this like that. Now that will be equal to 1 by C is 1 into 10 power minus 6 integral 0 to 5 I of t dt. Okay, so you know that I of t is taking the value 4 milliampere from 0 to 3 millisecond. It is taking a value equal to minus 2 milliampere for the interval 3 to 5 millisecond. So I can write this as 1 into 10 power minus 6 integral 0 to 3 millisecond 4 milliampere, or I can write as 4 into 10 power minus 3. This I can write it as 3 into 10 power minus 3. This is 5 into 10 power minus 3. Okay, dt plus, and for the remaining time period, that is from 3 millisecond to 5 millisecond, it is carrying a value, it is having a current of minus 2 milliampere. So it is minus 2 into 10 power minus 3 ampere. Okay, so integrate with respect to time. Hope you understand how we wrote this integral. Any doubt you can ask me. So once you know how to write this, then rest is mathematics only. So you should be able to write this much. That much is circuit network theory. So when we look at the question, we should be able to understand what is the question asked and what is the data given. And from the question, it is should be understood that we are asked what is the voltage. We are given the voltage across the capacitor. We are given the capacitance value and the current through the capacitor. So they should automatically come. What is the voltage across the capacitor? This expression should automatically come. Then only we will be able to write this. And when we look at the waveform, we can see that it is current, which is a periodic signal. So we should have a mathematical expression for this periodic signal, which we have written here. Then we can integrate it as per this equation that we have written. That is the voltage across the capacitor. Okay. So what is the final answer you are getting? How much voltage is coming? Are you getting like this? So here we can multiply 4 into 3, which is 12. And here you have 5 minus 3 is equal to 2. Then 2 into 2 is 4. So here we have 12. Here it is 4. And we are having a minus sign here. So it is 12 minus 4 is equal to 8. Okay. So within the bracket, you should get this value as 8. And for the power, it is into 10 power minus 3 into 10 power minus 3. So it will be 8 into 10 power minus 6 divided by 1 into 10 power minus 6 in the denominator. So you will get it as 8 volt. Are you getting like this? Any issues? Any doubts? Any doubts till now? Okay, if it is okay, then we'll move on to the second part of the question. So what we have found out is what is the voltage at 5 milliseconds. So when the current is this value of current is applied across the capacitor, we can see that at the end of the 5 millisecond, the voltage across the capacitor has become 8 volt. Okay, so that is what we have found out. So for part A of the question, it is asked find VAC, the voltage across the capacitor at t is equal to 5k millisecond. Okay. Now what is the voltage at 10 millisecond? What is the voltage at 10 millisecond? Any guess? Will it increase or it will remain the same? You can I will give one clue. You can look at this expression and you can make some guess. So if I take another time period, what will happen? I will have one more integral here, right? I will have one more integral from the time period that is from 5 millisecond to here. I have integrated from 0 to 3 millisecond, then 3 to 5 millisecond. Then if I one more time period of oscillation is happening here. Okay. So here I can see that I will have one more integral that is going to range from 5 millisecond to 8 millisecond. Okay. In that case, I have to again multiply, integrate it with respect to this. So integral from 5 millisecond to 8 millisecond, 4 into 10 power minus 3 dt. And for the time interval 8 millisecond to 10 millisecond, I have to integrate with minus 2 into 10 power minus 3. So what is the net value of this integration? The net value of this integration is resulting in an addition of 8 voltage for each cycle. Am I right? Are you able to understand what I'm telling? Or you can substitute this and find. So if you want to find out what is the VAC at t is equal to 10 millisecond, you can substitute this as 1 into 10 power minus 6, and the limit is from 0 to 10 millisecond, 10 into 10 power minus 3 I of t dt. Okay. So in addition to this, we'll have two more integrals happening. One corresponding to the positive cycle of the positive half cycle of the second cycle and the negative half cycle of the second cycle. So it will add another 8 voltage to the original voltage, so that we will have 8 plus 8 is equal to 16 volt, right? So the answer is that will yield to 16 volt. Similarly, if you take one more cycle, VAC at t is equal to 15 millisecond, another one more cycle is getting added. So that will be 16 plus 8, which is equal to 24 volt will be coming, right? So the voltage gets on increasing as we apply more and more cycles of this particular current. Okay, voltage is going to build, because for every one cycle, current is getting more charge is getting accumulated across the capacitor plates. Okay, so that is the answer to this part A. That is for every 5k millisecond, as k takes the value 0, etc., 0, 1, 2, 3, etc., the voltage keeps on building in steps of 8 volt. The part B is asking what is the value of a constant current IDC which can produce the same voltage across the above capacitor at 5 t is equal to 5k millisecond when applied at t greater than 0. So what is the answer for that? If I apply a constant DC current IDC, it should produce a voltage of 8 volt at the end of 5 milliseconds. So what is the modification I should make? Instead of this I of t, I should now replace it with I of IDC, right? So voltage, if I am applying ADC, if I am applying a current of, that is DC current IDC, IDC is IDC is applied. So voltage across the capacitor at t is equal to 5 millisecond will be 1 by C integral 0 to 5 millisecond, right? 5 into 10 power minus 3 IDC into dt. Okay, since this is a DC quantity, I can move it out of the integration, and I can substitute the values for the capacitor also, right? So I can write this as equal to 1 by 1 into 10 power minus 6, right? So 1 microfarad capacitor, and integral. Also I can take out this IDC outside of the integral IDC. within the integral, I have integral dt within the limits 0 to 5 into 10 power minus 5 integral dt, right? So what it will yield? What result it will come? So 1 into 10 power minus 6 and integral dt is t within the limit 5 millisecond to 0, right? So it will be into 5 into 10 power minus 3. So what is this? So that will be equal to 5 into 10 power 3 times IDC. Now the same voltage, that is the voltage at 5 millisecond. So now this, when this IDC is applied, it should produce the same voltage as the previous case. So that is what is mentioned in the question. So the value of a constant current IDC which can produce the same voltage across the capacitor at t is equal to 5 k millisecond. So what value of the current, DC current, which when applied will produce the same voltage as the previous case? So it means that it should be equated to the voltage of the previous case, which is equal to 8 volt. So this is equal to 8 volt. And we should find what is IDC. So what is IDC? It will be 8 upon 5 into 10 power 3. So 8 by 5 will be equal to 1.6 into 10 power minus 3 ampere. Or we can write is equal to 1.6 milliampere. Okay. So if you are replacing this current source is the periodically varying current source with a constant DC source. If you want to build up the same voltage 8 volt here, then I should have a constant current source which is delivering a current of 1.6 milliampere. So this is going to charge the capacitor to 8 volt at the end of 5 milliseconds. Second part, the third part of the question is telling compare IDC. So whatever we have found this current, you have to compare with the average value of IT. That is average value of this signal, this current, for a period of 5 millisecond after t greater than 0. So what is the average value of this voltage? So we can write the average value of this voltage. I of t is equal to 1 by t integral 0 to the time period. So what is the time period of that? It is 5 millisecond. Let me write the general expression first. So 0 to t it dt. So the time period is 5 into 10 power minus 3 integral 0 to 5 into 10 power minus 3 it dt. Okay. Now we apply the limits and substitute the functions suitably. So for 0 to 3 millisecond, it is having a value of it is having a value of 4 milliampere, and for 3 millisecond to 5 millisecond, it is having value of minus 2 milliampere, right? So we can substitute this here. So for interval 0 to 3 millisecond, 3 into 10 power minus 3, it is having a value 4 into 10 power minus 3, that is 4 milliampere dt, plus 3 into 10 power minus 3 integral over the remaining time period, that is 3 to 5 millisecond, which is minus 2 milliampere into 10 power minus 3 dt. Okay. Now we can do the integration. So we can take this 4 into 10 power minus 3 outside and minus 2 into 10 power minus 3 is outside. So what will remain is the integral of dt within the limits. So this will be 4 into 10 power minus 3, and here I have to integrate t within the limits. So what it will yield is 3 into 10 power minus 3, because integral dt is t itself, and I'm substituting that limit, upper limit, and the lower limit is 0. So there will be only 3 into 10 power minus 3. And for the second part also, I can substitute. I am taking out 2 minus 2 into 10 power minus 3, the constant outside of the integration, and inside the integral, I will have the upper limit 5 into 10 power minus 3 minus the lower limit, right? 5 into 10 power minus 3 minus the lower limit is 3 into 10 power minus 3. So that is 1 by 5 into 10 power minus 3. So here I have 4 into 3 is equal to 12 here, and here I am having 5 minus 3 is 2, 2 into 2 is 4, so this will be minus 4. So 12 minus 4 is 8, and the multiplying factor is 10 power minus 3 into 10 power minus 3. So it will be 10 power minus 6. Okay, so I have 8 into 10 power minus 6 with inside the bracket. So 8 by 5 is equal to 1.6 into 10 power 3, and this 10 power 6 minus 6 will get cancelled. So I will have 10 power minus 3 ampere. Or in terms of milliampere, this is equal to 1.6 milliampere. So what is your conclusion? The average value of the current for that period is equal to the DC current that we have obtained. This is equal to 1.6 milliampere. Provided the voltage across the capacitor is equal to 8 volt at the end of 5 millisecond. Okay. So this DC current of 1.6 milliampere we have found out for this particular case. It is the voltage across the capacitor. If you are applying this DC current, becomes 8 volt. So what should be the current? So that is 1.6 milliampere. And we have found that it is nothing but this 1.6 milliampere is nothing but the average value of the alternating signal, alternating current that we have already applied across the capacitor. So that is a relationship between the average value and the DC value in the case of the voltage across the capacitor. In the previous example, we have seen what is the relationship between the DC voltage and the RMS voltage when we are equating the power that is dissipated across the resistor. So hope you can appreciate the relationship between these two. So any doubts up to now?
No, sir.
Once you understand these concepts, you will be able to take out any numerical problem and you will have the confidence to work it out. So practice more numerical problems from any textbooks that is available, so that you will be able to work out more numerical problems, improve your confidence level. These are only indicative problems that I am demonstrating. Okay, now we come to the next portion, that is the non-periodic functions. Till now we are discussing on periodic functions. Now, for network analysis purposes, as well as for analyzing any system, okay, we have defined certain standard signals, and the purpose is to understand the transient response as well as the steady state response of the network. That is what is going to happen when we subject the network or the system to various disturbances. So we need to model the disturbances. So how can we model the disturbances? For that, we have certain standard functions or standard inputs that we can give to the system to understand this. One of the most commonly used standard function is called the unit step function. So it is defined as u of t is equal to 0 for t less than 0, and it is equal to 1 for t greater than 0. So it is graphed like this. So you should remember that this function, that is the unit step function, is undefined for t is equal to 0. Okay, so we don't know what is the value of this unit step function at t is equal to 0. It is not defined there, as you can easily understand from this equation. It is not less than or equal to, it is less than 0 and greater than 0. What is happening at t is equal to 0? It is not defined. That we will understand when we discuss the next standard function, that is the delta function. Why it is not defined anywhere there. Okay. So this is called a unit step function. From the unit step function, we can write any other step function. For example, I want a step function like this, that is from 0 to, it is shifting to say 5, a particular value 5. Then I can write this function as 5 times u of t. Okay, I can multiply this with that magnitude, so that I can write any step function. Okay, even I can multiply with a negative constant also if required. Okay, and that is not the purpose of this. Okay, another thing that I can do with this function is I can shift, just like I have explained for that sinusoidal functions. I can shift this function also. For example, I can delay this function u of t. So what I have done is I have shifted it across the time axis. It's a magnitude tau, time delay. So this is time delay, right? When I shifting to the right, it is called time delay. So let us take that I have delayed the unit step function. So I can write this as u of t minus tau. Okay, time delay is minus. Okay, so this is the delay operation I have done. Similarly, I can also uh, shift it towards the, or advance it, shift it towards the left or advance it. Okay, so if it's a 0 time instant, I can advance this signal by a magnitude tau like this. So that is also possible. So this is called time advancing. So how can I represent this? Since it is advancement, I have to add it. So it is t plus tau. Okay, so this is called advancing the signal. So just like sinusoidal function, I can shift it towards the left, right. I can modify the amplitude like multiplying with a constant. All these operations are possible with respect to the unit step function. Okay. Any doubts till now?
No, sir.
Okay. To appreciate why we are taking this, I will show one example. Okay, to illustrate the use of u of t, that is unit step function, assume that there is a switch S in the circuit. So, for example, it is mentioned that for up to t is equal to 0, this we can see here there is a one voltage source V naught, and there is a switch, okay, which can oscillate between these positions, which can toggle between these positions 1 and 2. Okay, and VAB is the voltage that is coming across the terminals A and B. Okay, so for example, the switch S in the circuit has been in position 1 for t less than 0. Now at a t greater than 0, it is moved to position 2. Okay, greater than or equal to 0, it is moved to position 2. So what happens is that this voltage V naught is now coming across this terminal A and B. Okay, so we'll have VAB is equal to V naught at t greater than 0. Okay, the voltage across VAB may be expressed as VAB is equal to V naught of U of t. So that is the purpose. So what we have done, like I told, when we are doing network analysis. So when I was discussing the analysis course, so there was one popular question: what, how we can practically represent a dependent current source or dependent sources? How we can represent? So actually, practically, it is not there. Actually, when we say that there is a, you cannot say that there is a current source. Then I said that you can put a sensor or an amplifier. Now that could be represented by a dependent source. That we will see in the future example also. When we see on Sunday lecture, most probably I will start with transient analysis. When I will discuss on mm, this, not Sunday, most probably on Monday class. Okay, that is when we discuss on the two-port network. So there is one concept called hybrid parameters. How we can represent. So in hybrid parameters is mostly used for representation of electronic circuits like transistors, etc. So in that we will see current sources. So a transistor could be modeled by means of an electrical network in which a dependent source is a part of that. So why we are doing this network analysis? We are modeling the situations like this. So in we cannot model a switch being thrown from this position, that is position 1 to 2, in the in and do the mathematical analysis, because it is a physical device, right? It's a physical device, so we need to represent it in terms of certain notations that we use in the network analysis in order to better understand the system and to study the system. Okay, so that is the purpose of these standard functions that we have studying at each stages. Okay, so how we can model this? So up to t less than 0, up to t less than 0, nothing is happening because it is like a short circuit. So no voltage is coming across the terminal AB. That is VAB is equal to 0. Now as soon as we throw the switch to position number 2, the voltage is coming. So how can we model this system? We can model this system by replacing this network. So now there is no switch. So it reduces the complexity of this network. So we can simply draw a voltage source which is having a voltage V terminal, which is having a voltage V naught of V naught into U of t, where U of t is called the unit step function, right? So this could be modeled like this. So can you write? Can you draw the voltage waveform? So when the switch is at 0, there is no voltage. So that is happening when t less than 0. So this is the time axis. So for t less than 0, there is no voltage. As soon as you throw the switch at position 2, the voltage, which is having a magnitude of V naught, is coming. Now if you observe, this is nothing but a step function. So this could be represented as V naught into U of t, right? Understood? Did you understand this? Are you following? I'm plotting VAB in the vertical axis. Follow or not? Any doubts?
No, sir.
Okay. So if you have understood, then I will modify this question. So instead of throwing the switch at t is equal to 0, what if I am throwing the switch at t is equal to 1? So how will it modify? How will this function get modified? If you can answer that question, then you have fully understood what I meant to say. You understood my question? So instead of throwing the switch to position 2 at t is equal to 0, I am throwing this switch to position 2 at t is equal to 1. So how can I represent this network? I will give some clue, some hint I will give you. So instead of throwing the switch at t is equal to 0, I am throwing the switch to position 2 at t is equal to 1. To some scale, let us say. So what is this function? Anybody? What is this function?
V naught U T minus 1.
Yeah, that's correct. Very good. So this is V naught into U of t minus 1. Okay. So replace this with V naught into U of t minus 1. Then we can model this circuit in which the switch is thrown to position 2 at t is equal to 1. Okay. So hope you will understand, you have understood what is the purpose of these standard signals. Okay. The switch, example, the switch in the circuit of figure 6.8a is moved to position 2 at t is equal to t naught. Express VAB using step function. So this is the answer that you have already given. So how can we model this? We can model this with a constant voltage source which is expressed as V naught into U of, tell me, what should I write here? This is terminal AB. So how can I write this? The switch is thrown to position 2 at t is equal to t naught. Okay, so at t is equal to t naught. So what should I write here? U of t?
T naught.
T minus t naught. Okay. Similar question only. If the switch in figure 68A is moved to position 2 at t is equal to 0 and then moved back to position 1 at t is equal to 5 seconds. Think and then answer. How can I write VAB? So initially the switch is moved to position 2 at t is equal to 0, right? So at that point, what voltage will come? When I throw to this position 2, if you have any doubt, you can draw also and see. Draw the waveform and see so that you'll be able to. So at t is equal to 0, the switch is thrown to position 2. So what is the voltage coming here? Across the terminal AB, VAB will be equal to and I throw this switch to position 2, what will be the voltage VAB? The battery will be included, right? If it is at position 1, there is no battery involved. So there won't be any voltage VAB. VAB will be equal to 0. When I throw this switch to position 2, this battery will come across, the voltage across this battery will come across here. So what will be VAB? Are you getting this? When I throw to position 2, what will be the voltage coming across terminals A and B? Say something, let it be a mistake also, no problem. All answers need not be correct answers. I am not getting, I'm not hearing, it's not clear. Somebody said something, but it's not clear. Somebody is writing V naught of U of t minus 1, V of U of t minus U of t minus 5. Okay. So that is correct answer. So when it is thrown to position 2, we get the voltage, which is V naught, and at t is equal to 5 seconds, it is thrown back to position 1 back again. So at 5 seconds, it is thrown back to first position so that there won't be any voltage coming across this terminal AB. So how we can write is, so if I write this is V of V naught into U of t, then I will have a voltage like this. It is going to be like this indefinitely. So I have to subtract this voltage at t is equal to 5 seconds. So I have to delay this unit step function by an amount equal to 5 seconds and then subtract it. So this is t minus 5. So this is how you can represent or model this particular situation in which the switch is thrown to position 2 only 5 seconds, only for 5 seconds, and then it is thrown back to position 1. Okay. Hope you all understanding. Next example, express v of t graphed in figure using the step function. It may seem that it is a sinusoidal function, but only one cycle is represented here. We need only one cycle of the sinusoid function. And for the remaining period, it is remaining at 0, as shown by this thick line. So how can we represent this function? So we can write this function as sine t. If I write it as sine t, if I represent it as sine t, it is a periodic function. It will have all the cycles in the uh, positive time direction as well as in the other period also. But we don't want this thing to happen. We need only this portion. Okay, so up to here only we require. Okay, that is for t is equal to up to 2 pi. It is required. So if we simply write s as sine t, then this is going to come. But we need only one cycle out of it. We don't need the negative side. Okay, so as soon as you multiply this sine t with ut, unit step function, all the negative regions are eliminated. So I have only this region. Like that, it is going to continue. So this is equal to sine t into ut. Right? But I need to eliminate this region also. From here onwards also, I need to eliminate this. So I have to subtract something. So I should delay this unit step function by an amount this much. Okay, by an amount 2 pi, and then I have to subtract this. So I have to delay the unit step function by an amount 2 pi, and then I have to subtract this. So this is how we can represent this function. Any doubts?
No, sir.
Okay, the next standard function, non-periodic function that we are interested in is called the unit impulse function. This is yet another important function that we will come across, especially to study about the transient conditions. This is more useful when we undergo the course on control system. So where we represent a system by its by its function, that is this function, system function, in which we define so the network function or the system function is represented as the impulse response of the system. That is when we subject the network to an impulse signal. So what is the response? Okay, that is how we can model the network. Now, what is the definition for this impulse function? So how it is obtained? So for that we have to consider a function like this s of t. Okay, so this is a function that is rising from 0 to 1 during the period capital T, and it is staying at that particular value for the remaining time period as t tends to infinity. Okay, so this is a function that we are going to consider. So I can define this function like I can write s of t is having a value. So that is equal to, how can I write this function? 1 divided by t into t, right? For t ranging from 0 to capital T. And it is going to remain at 1 for t greater than capital T. So this is this function. Okay. So which is 0 for t less than 0. Okay, one more value is required because we are not, we have to define what happens when t is less than 0 also. So it is 0 for t less than 0 and increases uniformly from 0 to 1 in t seconds. So that is represented by this uh, function, value of the function. And it remains at 1 for t greater than capital T. Okay. Now we can write its derivative. So its derivative could be written as dt of t. So when we differentiate 0, it is 0 for t less than 0. When we differentiate 1 by t into t with respect to t, it will be equal to 1 by t, and it will be the value for t ranging from 0 to t. And when we differentiate 1, it will be equal to 0 for t greater than capital T. So this is the function that we get when we differentiate s of t. So small d of t is nothing but d by dt of s of t. Okay. So when we graph it, it will have this shape like this. Okay. So it will have a maximum value of 1 by t for time ranging from 0 to t. For remaining time period, it is going to have a value of 0. Okay. So this is dt. So its derivative dt is a pulse of duration t and height 1 by t as seen in the figure. Okay. Up to here, I hope it is clear. Now what we are going to do is we are going to take the limit. So we are going to reduce the transition time. So this capital T is called the transition time for the initial function to rise from 0 to 1. Now we reduce this transition time. As we reduce the transition time, what happens to our function? So what will happen to, so what will happen to the derivative? And we have to limit it. So as t approaches 0 and we are limiting it, then what will happen to s of t and what will happen to its derivative d of t. So when we make this equal to 0, so we can see that as we reduce the time period, this slope is going to reduce right like that. So initially it will reduce, then it will reduce, then it will reduce, then as t tends to 0, it will be having in this slope is equal to vertical. It will become vertical. So we'll have s of t which will be represented by a unit step function. At that time, what will happen to the derivative? The derivative of this function. So when t tends to 0, so as t tends to 0 in this function, dt of t is now going to tending to infinity. So we can see that at the instant t is equal to 0, at the 0 instant. So that is the one of the reason why the step function is not unit step function is not defined for t is equal to 0. Okay, so that is defined only for this unit impulse function. So this will tend to infinity. Okay, this is derivative, because as t tends to 0, dt of t will be tending to infinity, whereas the area of this graph is going to remain the same. This is nothing but 1 by t into t, which is equal to 1. Okay, so that is called as an unit impulse function. Okay, so the derivative dt of t becomes a unit pulse delta of t with 0 width and infinite height. Okay, the unit impulse delta of t is shown here. The unit impulse or unit delta function is defined as delta of t is equal to 0 for t not equal to 0. So delta of t is defined only for t is equal to 0, and the integral of delta of t will be equal to 1. That is why it is called the unit impulse function. Okay, the area in this area under the delta function is equal to 1. Similarly, just like we did for the unit step function, we can multiply this delta function with a constant a. Okay, where a is called the magnitude, or it is otherwise called the strength of the impulse. Okay, so an unit impulse could also be delayed, like we did for the unit step. So I can write delta of t minus t naught also, which means that it is delayed. Similarly, I can write delta of t plus t naught, which is called advance. I can shift it left and right. So this is called advance in the time domain. Similarly, I can multiply it with some values to I can multiply a constant, say a, with to the unit delta function to get delta functions of other areas. So I have to increase the strength of the impulse. You multiply it with a constant so that you will have a larger impulse. So these things we can do to this function. Is it clear? In short, the delta function dt is defined for limit t tends to 0 of dt of t. So delta of t is equal to 0 for all t which is not equal to 0, as well as integral of this delta t for all the interval, for all the time interval is equal to 1. That is the area under this delta of t. So you know that what is integral of this function. Integral means the area under the curve. Okay, so area under the graph is equal to 1. So that is the definition for unit delta function. So this we need, okay, for our analysis purposes. So let us take one example. The voltage across a terminals of a 100 nanofarad capacitor grows linearly from 0 to 10 volt, taking the shape of function s of t. Find the charge across the capacitor at t is equal to capital T, the current in the capacitor at t is equal to 1 second, 1 millisecond, and 1 microsecond. Can you do this? So so here we are applying a voltage across a capacitor, which is going to linearly grow from 0 to 10 volt. Okay, 10 volt. It is going to grow linearly from 0 to 10 volt. Take in the time duration t. Okay, so this is the voltage across the capacitor. Let me denote it as Vc of t. Instead of St, I will represent this as Vc of t. We are asked to find what is the charge across the capacitor at t is equal to t. So as the voltage grows from 0 to 10 volt, what is the charge that is accumulated across the capacitor? So what is Q? What is the expression for the charge across the capacitor? Q. Anybody, can you give some hint? How can we find Q? One method is we can integrate the current, right? Q is the integral of I flowing through the capacitor, that is IC t times dt, right? So this is one method you can use. And we can write what is IC if we know what is the voltage across the capacitor. So if we know the voltage, I can write I is equal to C dVc of t. That is the voltage across the capacitor Vc by dt, derivative of the, because we know that I is equal to C into dV by dt. So here we are given that a 100 nanofarad capacitor and the voltage is growing linearly from 0 to 10 volt. Okay. So what is Vc here? I need to write this in a mathematical form. So how can I write Vc of t? Using the principles that we have studied, that is the unit step function, you will be able to write. So it is growing linearly from 0 to 10 volt, right? So how can I write an equation for this slanting line? Can you give me a clue? How can I write an equation for this slanting line? So basic mathematics, you must have studied about this. This is x and this is y. What is the equation of this line? This is the line y is equal to x. Y is equal to x. Okay. Provided the slope is equal to 1. So this is 45 degree and this is equal to 45 degree. Okay. So if I want some other slope, I need to change the inclination of this line to another like this. Then I can write this as y is equal to m into x, where m is the slope of called the slope of this line. Okay. Now if I want to shift this up or down, so I can shift it here, and the slope of this line is not going to change. So this is slope is equal to m itself. But here I have a y-intercept here, and this is c. The y-intercept is c. Then okay, this is c. Then I can write y is equal to mx plus c. Right. This we have studied in our basic mathematics. So using that similar lines, I can use that equation to represent a voltage. If represent this voltage for the region 0 to t. So that will be how much? What is slope of this line? That is 10 minus 0 divided by t minus 0. So that will be 10 divided by t into t. So if I write like this, then it will be a line that is going to be there from minus t minus infinity to t is equal to plus infinity. So it is going to go like this. Now I don't want this thing to happen. So how can I limit it? I limit it by multiplying it with u of t. So what happens is that the negative region is gone, but the positive region is now going to increase from 0 to t is equal to 0 to t is equal to infinity. Now how to solve that? So I have to subtract the unit step at a delayed time, which is t minus capital T. Okay, now what is happening? This line is cut short and only up to here I will have. Okay, so now it is only up to here. Now I have written the equation up to here, but the voltage is not completely defined. If I have to completely define, I have to mention something about here also, this thing also. How I can write this equation? Now to this equation function, I have to add that step function, which is having a magnitude equal to 10 into the unit step function u of t. Is it u of t? No, I have to delay this, right? I have to delay this with, because I need that unit step function from t is equal to capital T only. So I delay this step function by a magnitude equal to capital T. So delay is done by subtracting the delay amount. Okay. So this is that voltage function. Okay. So this is our VC, the voltage across the capacitor that is getting applied. So I have written this mathematical equation for this particular voltage wave. Now I can find out what is the current. The current across the capacitor IC of t is nothing but the derivative of this C multiplied with the capacitance value. So what is the capacitance value? It is 100 nanofarad. So it is 100 into 10 power minus 9. Okay, into d by dt of this particular voltage. So what is the d by dt of VC of t? So derivative of this first portion is 10 by t, right? And the derivative of the second portion is equal to 0, because this is a constant, right? And this is also a constant. Okay. So this will be equal to 100 into 10 power minus 9 into derivative of this is 10 by t into u of t minus u of t minus tau, right? So this is the current that is now flowing across the that is applied current that is flowing across the capacitor when we are applying this particular voltage. Okay. But the part one of the question is asking what is the charge across the capacitor at t is equal to capital T. So what is the charge across the capacitor? So for that we need this expression q is equal to integral 0 to t of this integral of this current. Okay. Now what is q? Charge across this capacitor is equal to integral 0 to t IC so we can take all these things outside. Okay. So when we take all these things outside, so that will be 100 into 10 power minus 9 into 10 by t, right? Now, no need of taking this thing, okay, because it's only a unit step function that is delayed here. So we can integrate this with respect to 0 to t of dt. So that will be t. Okay, so this will be equal to t. Now this t and this t will get cancelled from the numerator and denominator. So ultimately, what is the charge that is accumulated? It will be 100 into 10 power minus 9 into 10. So that is equal to 1 into 10 power minus 6 or this much of coulombs. Okay, 1 into 10 power minus 6 coulomb. It is nothing but 1 microcoulomb. So that is the charge that is stored across the capacitor when you are applying a voltage given by this. That is a voltage that is linearly rising to 10 volt and then remaining constant. So why take all these pains? There is one simple method. If we know the capacitance value and the voltage across the capacitor, we know that the voltage is linearly rising from 0 to 10 volt and is going to remain the same. So what is the voltage across the capacitor? It will be equal to 10 volt itself. So another equation we already know, q is equal to c into v. You can directly find out what is the charge. So c is equal to 100 nanofarad, 100 into 10 power minus 9 into v is 10 volt. So that is equal to 1 microcoulomb. So that way we can directly find out also, instead of integrating the current, finding the current across the capacitor and then integrating it like that. You can also go for that particular method. Okay. Whereas part B of this question is telling the current IC in the capacitor for t is equal to 1 second, t is equal to 1 millisecond, and t is equal to 1 microsecond. So what is the current that is across the capacitor for all these time instances? So we have an expression for the current here. So this is our IC of t. So we will use this expression to find out the current at various values of capital T. So I can take this value. So I need to find what is IC of t is equal to 1 second, 1 millisecond, and 1 microsecond. So t is equal to 1 second. So that will be equal to 100 into 10 power minus 9 into 10 divided by 1, which is nothing but equal to 1 into 10 power minus 6. So that is equal to 1 microampere. Similarly, if you need to find what is the current through the capacitor at t is equal to 1 millisecond, right? So this is capital T. Okay. So that will be equal to 100 so 1 millisecond. Okay. So 100 into 10 power minus 9 into 10 divided by 1 into 10 power minus 3. So for this t, that the current expression, for this t, you are going to substitute the various values. So now what will happen? So this will be 1 milliampere, okay, into 10 power 3. Similarly, IC when t is equal to 1 microsecond, so 100 into 10 power minus 9 into 10 divided by 1 into 10 power minus 6. So that will be equal to 1 ampere. Hope you understood how it is done. Any doubts in this? Hope it is clear to you. Any doubts? What is being done here? Okay. I hope you are saturated now. So let us stop it here then. In the next class, we will see what is meant by an exponential function. So similar to the unit step function and the delta Dirac or the delta function, unit delta function, we have another function, exponential function, but this is not used for modeling the network. This is only used for this function will get uh, as a response to the network. So we'll see how the response could be represented in terms of exponential. Then how we can plot this exponential function. Then we'll see what is meant by damped sinusoids. Then with numericals and all. Then we'll do some lot of further numericals to better understand all the concepts that we have studied. Okay. So that is, so these are the basics of this how these signals, what are signals that we are applying to the network, and how the network is going to respond. What is the voltages and currents that are coming across these various elements. So after that we will start on module 2, which is on Laplace transforms. So this is also a lot of questions are asked in the gate exams based on this topic. So we'll see how we can represent any network in terms of its frequency domain, and how the network analysis could be carried out in the Laplace domain, that is the complex frequency domain. Okay, so most probably we'll start with Laplace in the next class, that is Sunday evening, most probably. Monday we'll see what is meant by two-port networks. Okay. So meanwhile, if you are genuinely interested in preparing for gate exam, you should work out a lot of numerical problems, because there is no theory in gate exam. So it's only application of whatever knowledge. So whatever we have studied, you should be able to recollect what should be applied. So that will come only through practice. So variety of numerical problems you see, then you will be able to deduce which method you can apply. Okay. So today we'll conclude. We'll see on Sunday morning 8 o'clock. Okay. Good night, everyone.